welcome back. Now we'll be considering cardinality of sets and perhaps some further details about cardinality. Let's begin. For sufficiently small sets, such as those of finite cardinality, this notion can be made somewhat more explicit. Consider these formal symbols of a set including just slash marks, which are constructed beginning with the symbol slash, followed by its successor slash slash, obtained by a joining stroke, and then following that with its own successor slash slash slash. At each stage in this construction, the successor of one of these symbols is obtained by adjoining another stroke to that symbol. This initial symbol of just slash represents the cardinality or equivalence class of sets consisting of the sets that can be obtained by replacing the stroke slash by an element of any set. Its successor represents the cardinality or equivalence class of sets consisting of the sets that can be obtained by replacing the strokes by distinct elements of any set, and so on. These cardinalities, thus constructed, form a set N called the set of natural numbers. The natural number, that is, the cardinality represented by the symbol slash, is usually denoted by 1, so that 1 is the cardinality of X for any set X consisting of a single element. And if N is an element of the natural numbers, is the cardinality described by one of the symbols in this construction, the cardinality represented by its successor is denoted by N prime, and is called the successor of N. And in the customary notation, 2 is the successor of 1, and 3 is the successor of 2, and so on. In this construction, we see that the set we've constructed, the natural numbers, satisfies the piano axioms. There's an origin, namely the specified element 1 in the natural numbers, or slash in our previous construction. The succession operation, such that for any element A in the natural numbers, there's an associated element A prime in the natural numbers, which is the successor to A, such that A prime is never equal to A, and A prime is equal to B prime if and only if A equals B, and 1 is the successor of no element in N. Finally, induction, such that E is a subset of N, is any subset where 1 is a subset of E, and that A prime is an element of E whenever A is an element of E, then E is the whole set of natural numbers. This axiom of induction is merely a restatement of the fact that the set N is constructed by considering the successors of every cardinality already in N. Some consequence of the axiom of induction is that every element A except 1 is a successor of another element in N. Indeed, if E is the set of 1 union with the set of X, such that N is the X in N, such that X is a successor of some Y in the natural numbers, then it's clear that 1 is in E, and since if X is in E, then X prime is in E, then E is all of N. Usually, the natural numbers are defined by the piano axioms, since the equivalent for any set satisfying the piano axioms can be identified identically with the set of natural numbers by yet another application of the induction axiom. However, in this case, we didn't quite use that, but our set is defined and obeys the piano axioms. For some more detail on cardinality, we'll note that it is not asserted or assumed the cardinality of any set is actually a natural number, because we define the natural numbers in terms of cardinalities. Those sets with cardinalities that are natural numbers are called finite sets, while the sets that are not finite sets are called infinite sets. And we denote this by saying that a set S is infinite by writing the cardinality of S is equal to the infinity symbol. This is slightly strange, since it does not mean that infinity is the cardinality of the set S, it just means that S is not a finite set, since there are multiple types of infinity, as we will see. In particular, the set N itself is an infinite set. We see by definition of the natural numbers as equivalence classes of cardinalities that a finite set cannot be equivalent to a proper subset of itself. However, we do have the mapping that N of F from the natural numbers to the natural numbers excluding 1 that associates to every natural number N its successor is injective by succession and surjective, since we can always go forwards. So N is equivalent to N excluding 1, so N cannot be finite. we usually denote the cardinality of n, which is not a finite number, as Aleph null. So if A is any set that is equivalent to n, then the cardinality of A will also be Aleph null. A set A such that the cardinality of A is Aleph null is said to be a countably infinite set, while a set that is either finite or countably infinite is called a countable set. With that discussion of cardinality, thank you for watching, and next time we will continue with mathematical induction.